Welcome to this channel. If this is your first time of coming across this channel, kindly subscribe to this channel and click on the notification icon to get notified when we release videos so that you can see it. All right, what are we learning in this video? This video is a continuation of transverse wave. So briefly, we are going to look at sonometer, we are going to look at N correction and how we can apply them to solve questions. Without further ado, let's start the class. Now let's talk about end correction. What is end correction? Before we start learning end correction, we need to know some things, which is node and antinode. Let's quickly talk about node and antinode. These are the things that we have learned in the previous video when I was explaining wave, the terms that is used in wave, terminologies of wave. So we talked about node and antinode, where node is the stationary point in wave, while antinode is the maximum point in wave. Now for vibration of string, let me quickly draw that for string. Let's have the first harmonic for string. You have something like this and you have something like this. Now this point is node. Talking about this point is also node. This is the maximum point, which is antinode. We also have an antinode here. So this is antinode, this is node. Let me just draw close pipe like this. The first harmonic, fundamental frequency, fundamental tone. Now at this point is the node. This point is the antinode. Now take a look at this very well. For the formation of the antinode, it will be just right outside the colon, beyond the length of the pipe. So it will be formed outside. So that is what we know as end correction. In the analysis and designing of pipe, you need to take account for where the antinode will be formed. And that is what we call end correction. Now let's quickly analyze end correction. So let's have a closed pipe as shown. Now looking at this closely, we observe that the antinode is formed just right outside this pipe, the length of the pipe. So we need to take this into consideration when we are dealing with pipes. Now this is the length of the pipe. This is the end correction shown here, the distance between the end of the pipe and where the antinode will be formed. Now what will now be the actual length if you want to design the pipe? Now the actual length, when you take into consideration end correction, you have LA is equals to what? End correction plus the actual length of the pipe, the length that you want to use for designing of your pipe. Ending length for designing of your pipe, L, plus the end correction will give you the actual length you are going to use. Now for closed pipe, we only see that we have one end correction. Now how do you now find that end correction? You use this formula. End correction is equals to 0.6 multiplied by the radius of the pipe. Let's say you want to design a flute. Okay, you take into the consideration the length, intended length for your flute, and then you use this formula, the radius of the flute. Then you have 0.6 multiplied by the radius. That is the end correction you are going to take into account while designing your flute. Okay, now you have LA, the actual length you are going to use will now be the length, intended length plus the end correction. So you now have L plus 0.6 R. Okay, this E. That is how to find end correction of closed pipe. Let's look at open pipe. Okay, now let's have this for open pipe. Now if you look at open pipe very well, we are going to have two end correction, one for this end and the other for this end. It's very simple. Okay, the actual length that you will use in designing. So for open pipe, you now use the actual length will now be the intended length plus 2 end correction. 2 multiplied by end correction, you have one here, you have the other one here. So you have L plus, what's this end correction? End correction is equals to what? 0.6 R, isn't it? Now 2 end correction will now be what? 2 times 0.6 R, which is equal to what? 1.2 R. So that is why we have 1.2 R as shown. Now we have L plus 1.2 R. So that is N correction. Now you can go back to when we are doing, let me quickly do one here. In our previous video that was analyzing all this stuff for you guys. Okay, for instance, instead of using L that we have here in the analysis of relationship between length and the wavelength, you can use this actual length, which is what? L, for this one, L plus what? 2N correction. So you can use that. Now, E is the N correction, R is the radius of the pipe, and L is the length of the pipe. LA is the length of N correction, the actual length. Now we want to learn resonance. Before I explain resonance, let me quickly give you an analog of resonance. We all know that laughing is contagious, isn't it? Now, just imagine you are seated maybe in your house or in your room, in your class, anyway, and someone started laughing beside you. That person continues to laugh. Okay, which means that person is increasing the frequency of the laugh. The laughing is occurring at a particular frequency. Now the person continues to laugh and you are looking at the person. It will get to a point that you will now start laughing again. Coupled. Now someone is laughing, you are not laughing. You are looking at that person to get to a point at which you two will start laughing. What happened? Now, as the person is laughing, the laughing is occurring at a particular frequency. After some time, the frequency of the laugh will correspond with your own natural frequency of laughing. If you are the type that easily laugh, as the person starts laughing, between 3 seconds, you two will start laughing. If you are the type that you don't laugh easily, and the person continues to laugh over the time, the frequency is increasing. It will get to a time at which the frequency of the laugh will correspond with your own natural frequency of laughing. And you two, you now start laughing. That is the phenomenon that is known as resonance. So resonance occurs when a vibrating body, the frequency of the vibrating body now corresponds to the natural frequency of a close body, of another body or close body, thereby setting up the other bodies into vibration, thereby causing the other body to vibrate. That is what we call resonance. Now, resonance is similar to what we call induction in electricity, mutual induction. Okay. Now, a body vibrates, and the frequency of the vibration corresponds with the natural frequency of another object, and the other object now starts vibrating. That is what we call resonance. Example of resonance is when you have a vibrating body and you bring it close to a surface, let's say like a plank or a plywood, and you are going to be hearing a loud sound because the plywood also starts vibrating. That is what we know as resonance. Resonance. Okay, now we want to look at resonance in closed pipe. How can we have resonance? Now this is a practical setup. We are going to have a closed pipe as shown. One end of the closed pipe will be attached to a tap as shown, a tap that you can open or close. We want to pour water here, and we want to have a vibrating fork, a tuning fork. So we want to put it over here, and we want to observe the sound that will be coming out. There will be a particular point at which we are going to hear a loud sound. Once we hear a loud sound, we know that this is a resonance. So we have the fork here, and we have water inside this closed pipe. Now, as this tuning fork is set into vibration and we open this, don't forget this is closed pipe. The water surface will act just like a closed pipe. Okay. Now, some wave will be generated here due to the air. So, which means vibration of air in this closed pipe. Now, as the water is reducing, it will get to a point where we are going to hear a loud sound. Now, what happened at that particular spot? It means that the frequency of this tuning fork as correspond to the natural frequency of closed pipe. Now, the water surface is going to act as a point for node. Okay, so let's do it. So it means that it corresponds to the what? First harmonic frequency. Okay, don't forget this. So this is end correction. I've explained end correction. Now the frequency correspond, because we are hearing a loud sound now, it means that we now have resonance, which corresponds to the what? First harmonic of this one. Now it's very simple. The length from here to here will correspond to the length of the pipe, because this one water surface is acting as the other end. So we have L1 here. If we continue to reduce this water, it will get to another point at which you hear a loud sound again. So which means that it corresponds to the next natural frequency of this colon, and that is what? Second harmonic that we can see here. If you continue like that, it will get to a point that you are going to hear another loud sound, which corresponds to the word third harmonic, as you can see here. So this is called resonance. Okay, now let's quickly do the analysis very fast. We know that for first harmonic, come here, if you have forgotten, this one is what? From here to here, this is 1/4. So you have what? L is equals to lambda over 4 that we can see here. Okay, so which means the L1, this L1 can also be what? L1 plus endpoint. So if you like, you can have it that way. So will be what? Lambda over 4. Okay, so when you look at this, we know that this one is what? 3 lambda over 4 for L2. Okay, now when you now find the difference between L2 here, the difference between L2 and L1, just try to find the difference. When you find the difference, you are getting what is being shown. So you are getting this. This is what you are going to get. 3 lambda over 4 minus lambda over 4. So let's continue. So when you solve that using fraction, you are going to get lambda over 2. You are still asking me how is it lambda over 2? LCM is 4 here. 4 in 4. So you now have 3 lambda minus lambda. So you have 2 lambda over 4, 2 lambda over 4, and that is lambda over 2, 2 here, 1, 2 here, 2. So you are going to get this. Okay, now let's continue. So which means that you can make lambda squared of formula. Once you make lambda squared of formula, you get this L2 minus L1. That is what we want to do. Now when you do that, you are going to get that guy that is being shown. So which means that what? 2 L2 minus L1 is equals to lambda. Okay, so you recall that V is equals to F lambda. When you substitute the value of lambda, so when you put this guy, inside this formula, so you get what? 2 multiplied by this, 2F L2 minus L1. So you can even play with this formula, make F squared of formula. When you make F squared of formula, you have V over 2, open brackets, L2 minus L1. Let me say this. If you are writing exam and they are telling you the resonance, they can ask you to find the resonance frequency. So if they are asking you to find the resonance frequency, you can use this method, this formula. Okay, so they can tell you that the first resonance occur at a particular length. So they will give you the second resonance occur at a particular length. The question, they will give you the velocity of sound. In a question, how do you apply this to solve question very fast? It's very simple. Now they can give you a question and they'll tell you that in a tuning fork experiment and closed pipe, first resonance occur at a particular length. That means they are talking about L1. Okay, they will give you. They will tell you that the second resonance occur at another length. That is L2. they can give you the velocity. Don't forget, they can give you the velocity of the sound. Okay? And they will now ask you to find the frequency of the vibration. The frequency of the vibration. So you just go ahead and do V over 2 L2 minus L1. Very fast. If you are writing your UTME exam or WAEC exam or any other exam, you can apply that very fast to solve. Sonometer monochord. Now, sonometer, which is also known as monochord, is an instrument that we can use to show the relationship between the frequency of vibration of string and the length of the string, the mass of the string, and the tension on the string. So if you want to demonstrate how the frequency of the wave generated by string is related to the mass of the string, the thickness of the string, so mass of the string, the length of the string, how long it is, and the tension, how tight the string is. So you can use sonometer. Now, sonometer is very useful in designing of string instrument, just like violin, guitar. So we are still going to look into that. This is a sonometer. Now we have a table here. This stuff here that you can see is called sonometer. This is the sonometer here. Now, sonometer wire, which is usually a melter or a polymer string, a polymer, just a single one, that is what we call monochord. So at one end here, it will be fixed here to this point. Now it will run over two wedges. So we are going to have two wedges like this. Now the wedges, we just provide fixed points so that this thing we can vibrate over this two wedge so that we can know the length of the string that is vibrating. Now it's going to extend outside over a pulley like this. We have a pulley here. Now at the other end of the string, we can attach different weights to provide tension in the string, how tight the string is going to be. Okay, then we can plug this and listen to the sound. Okay, the one that is tiny is telling you high frequency. The one that is not tiny, we call it low frequency. And let's see how this is related. Okay, now before we perform the experiment, let's quickly look at velocity of transverse wave. How can you find the velocity of transverse wave? Now it's somehow relating to sound, but it's different. Okay, the wave that is generated in the vibration of string is transverse and stationary. It is transverse and stationary, not longitudinal wave. The wave that is generated by string, vibration of string, it is not longitudinal wave. It is transverse wave and stationary wave. Okay, for transverse wave, the velocity of the wave is equals to root of the tension. This time around, it is tension, okay, divided by the mass density, mass per unit length. That is what we call mass density. Now you recall that velocity of sound wave in material medium is what? Root of what? Elastic modulus divided by what? Density. Okay, if you have liquid, just like water, is going to be what? Root of what? Bulk modulus divided by density of the liquid or fluid. If it is solid, elastic modulus or modulus of elasticity divided by density. But for transverse wave, the velocity of the wave is equal to root of tension, for instance, in the string divided by mass density. Okay? Okay, where T is the tension in the string and mu is the mass density, mass per unit length. Okay? We all know that V is equals to F lambda. So F will be equals to what? V over lambda. We know that V is equals to root T over mu. So you can substitute that inside this formula. So you have F is equals to what? Root T over mu divided by lambda, this one. So F will have what? Root T over mu times 1 over lambda. When you change this one to multiplication sign, you find the reciprocal of this one. So at the end of the day, you are going to have what? come back here. Look at these two wedges here. String is running over it. It's going to have a particular length from here to here. So when you pluck it, it's going to vibrate. Abi? So which means we are going to have this pattern of vibration, and this is called what? First harmonic fundamental frequency. Okay, you want to find the fundamental frequency, first harmonic, that will be produced with this certain length. Now it's very simple. We know that this pattern is what? L is equals to lambda over 2. Okay, so lambda is equals to what? 2L. So when you see lambda inside this formula, you can put 2L. Yeah, put 2L. So you have root T over mu times 1 over 2L. Bring out 1 over 2L. So you have 1 over 2L root T over mu. If you don't want to use mu, you can use M, but recall that M here is mass per unit length. Mass of the string divided by the length of the string. In this experiment is going to be the what? The total mass of this string divided by the length from here to here. So that is the mass density. Total mass of this string divided by what? The length of this string from here to here. Okay? This is our formula over here. Now let's do some kind of experiment to verify this formula. Okay, let's see if this formula is actually correct. Now, we will vary the length, we vary the tension, and we vary the thickness, and we hear the bang. Okay, now let's increase the length. So which means we want to slide this wedge. This wedge can be slide. Don't forget that for sonometer, we have a graduating table here. So you can easily slide your wedge so that the length of the vibration of this string can increase. Okay, when you slide it, you increase the length like this, and you pluck it. You are going to hear a sound that is low in pitch compared to when this wedge is a little bit closer. So the frequency will reduce. So which means that frequency is inversely proportional to length, and we can see it from this formula. Just go back here from this formula. So now from this formula, you can make K sort of formula, because F will be equals to what? K over L. So we have, when you cross multiply, FL is equals to K, F1, L1 is equals to F2, L2. If all other parameters in this formula are constant, so you have F1, L1 will give you F2, L2. Let's increase the thickness of the string. Automatically, you have increased the mass per unit length. Okay? When you do that and you plug this string, you are going to hear a sound that is having a low frequency. So, which implies that what? This one is also inversely proportional. And look at this formula. We can see that it is inversely proportional to the what? Root of M. Okay? If you try to use your mathematical knowledge, F is equals to K over root M as shown. So K is equals to F root M. We're going to have F1 root M1. We give you F2 root M2. What if you increase the load here? So which means you increase the tension and you plug this. The sound that you're going to hear will be high compared to the previous one. So which means the frequency will increase. Now, what is the relationship between the tension and the frequency? You can see it here. It is directly proportional to the root of T. So we can see that as well. So F is directly proportional to the root of T. So F is equals to K root of T. So when you make K sort of formula here, K is equals to what? F over root of T. Okay, which means constant. F divided by root of T is always constant. So you have F1 root T1 will give you F2 root T2. Okay. Summary of what we have learned using this sonometer. We all know this formula. F is equals to 1 over 2L root T over M. And we can use this formula. Coming from this, F1 over F2 is equals to L2 over L1. Please master this formula down. This same frequency, F1 over F2, is equals to what? Root M2 over root M1. if all other parameters are constant for this. If all other parameters are constant for this. Lastly, you can also have what? F1 over F2 is equals to root T1 tension 1 over root tension 2. These are tricks for solving some question very fast depending on the nature of the question. Okay, now we all know that T is the tension in the string. Tension is in what? Is in Newton. We all know that mu, which is still the same thing as mass. This mass that we talked about here is mass density, mass per unit length. So we know this, F is equals to this, and we know all this. Alright, that is all for now. Make sure you watch the next video just now. The next video, we are going to solve so many questions applying what we have learned in this video. And if you haven't subscribed to this channel, subscribe to this channel. Click on the notification icon to get notified when we release an insightful video. You can also check out the physics playlist on this channel to watch some of our videos that we have released. All right, thank you for watching. See you in the next video. Bye for now.